session అయిపోయింది. ఓకే, అంటే we have
Could
to
not
discuss.
explain Feynman effect line uncertainty అని చెప్పారు సార్.
యా కరెక్ట్. ఇక మనకి ఆల్మోస్ట్ ఇక Bose theory over. Sommerfeld theory is not there within the syllabus, so no need to discuss about elliptical orbits and consideration of the nucleus and electron as a double star system. Means few modifications they made none later. These orbits and means why the Bose theory failed, even though almost majority of the things explained here. Just a few drawbacks we found there. Okay, because of number one, by assuming the orbits as circular instead of elliptical. Okay, first drawback. And second drawback here, he assumed that nucleus will be at rest at the center and the electron only revolves around the nucleus. That is the second drawback, what the mistake the Bohr did here. First mistake, by assuming the orbits as circle. And second mistake here, nucleus is assumed to be at rest, but actually nucleus and the electron, they revolve one around the other like double star system. Nana. Okay, like here the electron suppose moves from here to there, the nucleus also moves from there to here about their common center of mass. Okay, double star system in first year we discussed. Okay, this will be the circular motion of nucleus and this will be the circular motion of the electron, like this. For both there will be common center. The center is not at the center of the nucleus, it is along the line joining between them. If you make these two changes here, one the orbit, number two the fixed nucleus concept, if you change the two, you will get whatever the practical observations, okay, you can explain with the theory. Kapati, this much depth is not there within our syllabus, that's why we are not discussing all those things. Okay, this
Sir,
part is out of syllabus. Yes.
సార్ ఇప్పుడు ప్రస్తుతం యూస్ చేసే అటామ్ స్ట్రక్చర్ లో న్యూక్లియస్ కూడా రొటేట్ అవుతుందా?
Yes, it is not at rest. And one more thing, a nucleus is also spinning.
Okay, sir.
Not only rotating, it is spinning. Electron is also not only rotating, it is spinning.
Like Earth, no, sir.
Earth laga. Spinning and rotating, and the nucleus is also spinning and rotating. Okay, ఇది కొద్దిగా modifications what they made. ఇది మనకి కాస్త ఏదైనా if you go beyond the scope, then we can discuss.
Good morning, sir.
Time లేదు, మనకు ఛాన్స్ లేదు. Yes, Mr. Bhargav, good morning. That's why here we are not discussing those out of syllabus concepts. Okay. Now we are coming to within the syllabus concept, that is the X-rays concept. Okay, akkadi nunchi skip ayi directly we are coming to here X-rays. Okay, in this X-rays, what the modifications they made to the Bose theory? Okay, from X-rays. ఆయన చెప్పిన థియరీలో ఏం మోడిఫికేషన్ చెప్పారు అన్నదాన్ని. These X-rays actually found during that time only while studying the cathode rays. Okay, what I explained in dual nature chapter. Their cathode rays, okay, they found one tiny particles, electrons. They travel almost equal to the speed of light in the discharge tube, comparable to the speed of light. And here, suppose they hit the anode. If you place the anode opposite, actually they placed the anode somewhere here. If you place the anode here, and that is made of like a high melting point. Okay, like molybdenum or tungsten. Okay, this is one surface. Okay.
Sir, X-rays ఇంకా gamma rays ఒకటేనా సార్?
X-rays, gamma rays ఒకటేంట్రా? ఆల్రెడీ స్పెక్ట్రమ్ చెప్పాను కదా మీకు నేను ఆ చాప్టర్లో. ఎక్స్రేస్ గామా రేస్ ఒకటే.
ఐ మీన్
ఎక్స్రేస్ వేవ్ లెంగ్త్ గామా రేస్ వేవ్ లెంగ్త్ ఎంత చెప్పాను రా? అందరికి ఎవరికైనా గుర్తుంది అది? తయారైపోతే ఎట్లరా?
Sir, 10 nanometers.
10 nanometer means 1 angstrom, what you are saying.
Yes, sir.
1 angstrom or inco a little bit 0.1 angstrom. You can take
0.
up to there the X-rays. Yeah.
0.01 nano.
Okay. Less than those wavelengths, they are gamma rays. Gamma rays have least wavelength, followed by X-rays వస్తాయి.
Yes.
ఓకే, గామా రేస్ ఎక్స్రేస్ ఒకటే అని అడగకండ్రా. ఇంత చెప్పిన తర్వాత రెండు ఒకటే అంటే ఎట్లా చెప్పు?
ఓకే
ఓకే భార్గవ్.
ఓకే సార్.
Right. Here, this is one target what I placed, a bit inclined, making an angle of some 45 degrees here. They found in the discharge tube ikkada. Okay. Suppose if you maintain some potential difference, okay, and here this is for the acceleration of electron. V is the potential difference maintained between these two, negative and positive. V is the accelerating potential, PD. To accelerate that electron. Okay. By that acceleration, before hitting that target, having high melting point, before hitting here, the velocity of electron, where V is the velocity of electron, this is the velocity of electron. Okay, that V, how much if they ask before hitting, we can say very easily. Accelerating PD is V, means by that work done is equals to VQ. That is converted into kinetic energy, half mv square. Okay, by this you can calculate the velocity of hitting electron. Okay, and this is the energy acquired by the electron here. Okay, that electron after hitting, and that electron penetrates the matter inside, they found here the matter, whatever you are taking here, like tungsten and molybdenum, they found using the collision principle, 45 degrees means with 45 degrees, instead of electron, they found some emission of energetic particles from here, from the metal. Okay, they found using the Bragg spectrometer that already I told. Okay, it is used to detect the invisible rays. Okay, so here they found these rays, what they observed are unknown rays named as some X rays. X means X stands for unknown rays. Okay, by that time, that's why they named it as X-rays. Okay, who are these X-rays? And again, they found some deviation in their experiment. Actually, they started this experiment here. Who? The scientist Röntgen. Perinara?
No, sir.
No, sir.
No, sir.
Actually, Röntgen started this experiment to study the cathode rays, properties of cathode rays, after finding out the cathode rays. But in that experiment, he found those electrons, suppose hit some anode, okay, he found some unknown rays are coming out of. Means by that time they don't know they don't know about these wavelengths coming out of that substance. Why? Because they have lower wavelength. By that time they knew up to only this ultraviolet region. అంటే అంతవరకే తెలుసు. అల్ట్రావైలెట్, విజిబుల్, ఇన్ఫ్రారెడ్, ఇక హయ్యర్ మైక్రోవేవ్స్, రేడియోస్ వాటి తెలుసు, కానీ లోయర్ వేవ్లెంగ్స్ దే డోంట్ నో బై దట్ టైం. Whereas he found the wavelengths which are less than these X-rays have the wavelength less than the wavelength of ultraviolet rays. Okay. అప్పటికి ఇంకా తెలియదు కాబట్టి దే నేమ్డ్ ఇట్ యాజ్ సమ్ అన్నోన్ రేస్. అన్నోన్ మీన్స్ ఎక్స్-రేస్. ఓకే, వీటి తర్వాత ఫైండ్ అవుట్ చేసినవి గామా రేస్. ఓకేనా? గామా రేస్ దే ఫౌండ్ ఇన్ రేడియో యాక్టివిటీ. నాన్న రేడియో యాక్టివిటీలో ఫైండ్ అవుట్ చేశారు. దే ఫౌండ్ దోస్ గామా రేస్. ఎస్, ఎనీ డౌట్?
Sir,
ఎస్.
sir, but current will also flow now to the circuit, sir, when that electron hits the anode.
Obviously.
Oh. And sir, we'll
That
get
electron still able is still yes.
and we'll get one more race called X-ray. That's it.
This is energy, Nana.
Okay, okay, sir.
Energy coming out of the X-rays are not particle rays. X-rays are energetic particles. Means
Okay.
energy.
Yes, sir. Okay, sir.
That's they found some high energy. Why? Because lower wavelength.
Okay, sir. Yes.
Okay.
Yes.
Radioactivity, in that also they found high energy rays. They are named as gamma rays. So in between gamma rays and UV rays, some other wavelengths they found. Who
Okay,
are
sir.
those wavelengths? We don't know. So unknown rays. Those rays are named as X-rays.
Okay, sir.
Okay, right. So these X-rays, why they are emitting when the electron penetrates the matter? Highly accelerated electron penetrates the matter. Why we are getting the energy from the matter? Okay, that's why he stopped here doing the experiment, means studying the properties of cathode rays, and he focused more on these energetic rays. Means he stopped studying the penetration of electron and blah blah blah, and he studied these X-rays, the Röntgen. Okay, and he explained the theory behind why these X-rays are coming out like this. Okay, here when after finding out the nucleus and atom, Nana, okay, he got some idea and he tried to explain. Okay, after finding out the atom, he assumed like this. This is the nucleus, and of course this is the atom. Okay, and this is one atom inside the substance, and it is the nucleus. And suppose this is the electron trying to penetrate the matter, means entering into the atom, just like the alpha ray scattering of Rutherford's experiment. The difference between the two is, in alpha ray scattering, this is the nucleus, what he assumed Rutherford, and alpha particle is a positively charged particle. That's why here Rutherford assumed that the alpha particle will go like this. Okay, because of repulsion. But in this case, Röntgen explained that because of attraction, okay, after penetrating the atom, this electron here because of attraction, it may deviate like this. Now the difference you observe, Nana? Just like alpha is scattering. Okay, it is
Yes.
deviated like this. Yeah. While deviating because of attraction, it is coming close to the nucleus here. Okay. While deviating, he said because of change of the direction of electron, it loses some energy. That energy continuously until it comes out of the substance, continuously it emits the energy. That energy you are finding out here with different wavelengths. Okay, those wavelengths, all collection of those wavelengths called as X-rays. Okay, so what he said, because of change of direction after entering the electron into the atom, better with it after penetrating. After penetrating the atom, the electron loses the energy continuously. Until it comes out of the substance. Okay. The collection of next point. The collection of different wavelengths results to the spectrum, to a spectrum called as continuous X-ray spectrum. Okay, this is the story what he said. Means keep in mind, while penetrating continuously it loses the atom energy, means we are considering the atom as one spherical substance. The electron should hit the atom and should penetrate into. Means first of all, it should possess the energy which is capable to penetrate the atom. Otherwise, it collides the atoms and stops there only. Are you following my logic?
Yes, sir.
Means the here the surface what we are assuming for the atom behaves like a membrane. Okay, like how we suppose when you drop a bucket into the well, there at the surface, so initially the bucket won't dip into the well. First of all, it floats at the surface, and after taking some water into the bucket, then only it sinks into the well. Correct, Nana? Even though that is a liquid.
Correct.
Liquid look is the solid. The solid easily dips inside, but that floats first, means the membrane what formed at the surface stops dipping that bucket, even though that is iron heavy bucket. Okay, and then later slowly it dips. In the same way here, the electron can't penetrate immediately. That behaves as a membrane, the surface of atom, and stops penetrating. Means there it loses some energy. That energy he said here. Okay, as continuous X-ray spectrum. Okay, collection of different wavelengths. Means you have to understand that why, yeah.
Nothing.
Here it loses some, it loses the energy and again tries to enter into the another atom, again loses some energy, again enters into the other atom, again loses the energy, and continuously here it is changing its direction and losing its energy. Now you understood this concept, Nana?
Yes, sir.
Now that spectrum intensity and wavelength, suppose if you draw practically what they observed for this continuous X-ray spectrum, like this. This is continuous X-ray spectrum, and here intensity. Intensity means how many number of wavelengths collected at one particular wavelength. Okay, means how many same number of wavelengths they found at one particular time. Okay, that is intensity and wavelength. Okay, they drew one graph, and here this graph they got like this, not linear graph. Okay, again here this type of nature of graph, it is just like a hyperbola, no, hyperbolic curve. Okay, sorry, not hyperbolic, exponential curve. This is the curve is exponential. That exponential curve here, why you got exactly identical to the same intensity wavelength graph for black body radiation. Same type you got here. Okay, so this one also, first again, not Röntgen, the Planck observed, and here he explained using his quantum theory. Observe here, we are getting third support to the quantum theory. Okay, already I told black body radiation. Sorry, not third support, fifth support, I think. Black body radiation. Number 2,
Photoelectric effect.
what is photoelectric effect? Number 3, Compton effect. Number 4, this Bose theory. Supported Bose theory also you can explain using the quantum theory only. And number 5, even here X-ray spectrum also. Okay. Planck here he found this relation using the quantum theory, the exponential equation. That's why the graph is exponential, and he found like this. Okay. And here in this graph, observe the intensity is almost 0, means minimum at one particular wavelength. Okay, and for the whole graph, observe exponential means it never touches the x-axis. All of you know that it extends up to infinity. Here lambda tends to infinity, but the graph is not started from origin. Not started from origin means you are finding out some minimum wavelength. Okay, that minimum wavelength in black body radiation we found at one particular temperature of a star. And from there we found lambda minimum is inversely proportional to temperature, so that lambda minimum into T is equals to constant, which is called as, in heat chapter, heat and here thermodynamics, heat and thermodynamics. What is it? What is it? This equation, Nana? Evarkaina gurtunda? Anyone can recollect? At least one person. Oh, very good. Called as Wein's displacement law. Okay, in black body radiation. Means with the increase of temperature, they found the minimum wavelength of exponential curve decreases. ఇలా వస్తుంది next curve. నెక్స్ట్ కర్వ్ ఇలా వస్తుంది. యూ విల్ గెట్ ద కర్వ్స్ లైక్ దిస్ నాన్న. అట్లీస్ట్ ఈ కర్వ్ గ్రాఫ్ చూసారా
Yes, sir.
in blackboard? Yeah. So the minimum wavelength decreases with the increase of temperature of the star. Their inversely proportional temperature, and there he found, Wien, the scientist Wien found that's why it is called as Wien's displacement law. Same type of observation here we are finding out. Okay, ante malli black body radiation type of curves we are getting here in X-rays. Okay, and here this one at one accelerating potential. Here accelerating potential we took V na. And
Sir.
here what he said, W is equal to VQ. You got, this is the energy of electron, and that energy lost at one particular collision, means at the first collision only it loses all of its energy VQ. Okay, and that comes to rest, half mv square becomes 0, then VQ energy will be lost out. Means electron is not captured by the atom and not coming out of the substance, suppose stopped inside. Then what he said, whatever the energy acquired by the electron, which is VQ, is converted into energy. According to quantum theory, that energy is equals to h nu, like only one photon. Is it correct, Nana?
Correct, sir.
Yeah. So in a single collision, straight away it loses all of its energy. You will get one h nu, and here the h nu, write it as hc by lambda. Here h constant, c constant, and q, charge on electron, is also constant. Why? Because electron is striking the atom. V and lambda, energy is maximum, means lambda is minimum. Is it correct?
Correct, sir.
Total energy is converted into only one photon, not n number of photons. One photon energy is maximum, so lambda is minimum. So lambda minimum is inversely proportional to V. This is what I am saying. Exactly identical to Wien's displacement law. They are inversely proportional to temperature, here inversely proportional to accelerating potential. Means I think you understood a bit here. Oh, we are getting same type of curves like black body curves. So clarity vachinda nana?
Clear, sir.
Yes.
Right. So next curve, with the increase of potential, you will get a curve like this, like in black body radiation. Next curve you may get like this. And third curve you may get like this. Like this. All are exponential curves. And you can identify that the lambda minimum is shifting back here. Like this, lambda minimum is shifting with the increase of potential. Okay, from here to there. This one what they observe, Nana. Okay, so that point what I am writing here in the next page. During the collision, if the electron loses all of its energy as a photon, then V into Q is equals to 1 h nu, I write. That implies V into charge on electron is E is equals to 1 h nu is C by lambda minimum. This is actually nu maximum. Okay, that implies lambda minimum is equals to, I am getting the equation, hc by E into V. Again, hc by E value I already told in photoelectric effect. That shortcut is
1340.
1240, no? 1340.
1240.
1240.
Sorry, sir,
1240
1240.
by V in nanometer.
Nanometer.
Yeah, in nanometer. And this is equals to 12,400 by V, not in nanometer. This is in wavelength is in
Armstrong.
angstroms. So you can use the same shortcut here also during the X-rays, that too particularly in continuous X-ray spectrum. Okay, so this is the story about the continuous X-ray spectrum, and here you can observe one more point. What the intensity is maximum here in the graph, here in the second graph, and here in the third graph. These are the maximum intensities. Okay, that is non-uniformly changing, you can observe there, but corresponding wavelength, if you see, that changes similar to lambda minimum. How the lambda minimum changes with the increase of V, that lambda also changes lambda of I max. That also changes identical to lambda minimum. That's why when you come to exam, they may ask either find out lambda minimum or the wavelength of maximum intensity. That also you can use the same formula, HC by EV, that is equals to 1240 by V in nanometer, and that is equals to 12,400 by V in angstroms. So later,
Sir.
don't blame me. Yes.
Sir, one doubt, sir. This
Yeah.
we wrote V is equal to HC by lambda minimum. Means always that energy won't be maximum. Sir. Sometimes it may be minimum or somewhere in middle also.
Yeah, that's why when you get the minimum wavelength, that time only we are getting this equation 12,400 by P. Only
Yes,
to find out the minimum wavelength, we use this equation.
Okay, sir. And sir, one more
Understood?
doubt,
Okay,
sir.
now Nikhil Guru. Yeah.
And sir, one more doubt.
Tell now.
Yes,
Yeah.
intensity depends on potential, sir. The intensity.
Yeah. Intensity curves, they depend upon the applied potential. So that's why you got different intensities here
Okay, sir.
for different wavelengths.
Okay, sir. Clear, sir.
Okay, at one particular intensity, you observe here the wavelengths are not same. You can find
Yes,
out
sir.
different wavelengths. Yeah.
Okay, sir.
సార్
Right.
సార్ మీరు ఇక్కడ రాస్తారు కదా సార్ సెకండ్ ఫార్ములా లాంబ్డా 5 మ్యాక్స్, అది దాని ఫార్ములా నెక్స్ట్ పేజ్లో అది ఒకసారి ఎలా చేస్తారో ఎక్స్ప్లెయిన్ చేయనా మళ్ళీ?
ఏం లేదు. It's for the maximum intensity. What is the wavelength you are finding out here?
Yes, sir.
Am I right?
Yes, sir.
It is coming identical to lambda minimum. Adi vadanedi. How the lambda minimum changes with V, lambda 5 max also changing identical to like that. Identical to each.
అంటే రెండిటి చేంజ్ డెల్టా వాల్యూ సేమ్, అంటే డెల్టా లాంబ్డా మినిమం ఈక్వల్స్ టు డెల్టా.
యా అంటే నువ్వు అడగాలనుకున్న డౌట్ నాకు అర్థమైంది సార్. హియర్ లాంబ్డా ఆఫ్ ఐ మ్యాక్స్ లాంబ్డా మినిమం కి ఒకటే ఫార్ములా అంటే ఆర్ దోస్ టు ఈక్వల్, అదేగా నువ్వు అడగాలనుకున్న క్వశ్చన్?
అదే సార్ డౌట్.
నువ్వు అడగాలనుకున్న వాళ్ళు చెప్పింది ఏంటంటే ఈ లాంబ్డా ఆఫ్ మాక్సిమం ఇంటెన్సిటీ అప్పుడు ఎలా చేంజ్ అవుతుందో లాంబ్డా మినిమం కూడా అలాగే చేంజ్ అవుతుంది. That's why you can find out. Yeah. అంటే డెల్టా లాంబ్డా ఫైండ్ అవుట్ చేయడానికి యూజ్ అవుతుంది అనేది. అర్థమైందా?
అండర్స్టూడ్ సార్.
రైట్. గుడ్. బాగానే ఐడెంటిఫై చేసావు. ఓకే. అండ్ దెన్ హియర్ Next, what I'm going to discuss in the continuous spectrum, what the points he gave in exam, the range of wavelength, okay, in continuous X-ray spectrum, is, okay, suppose given like a question, options, option 1, okay, 0 to infinity, option 2, lambda minimum to lambda maximum. This was the question given already, Nana. Advanced adigina question ID. Number 3, 0 to lambda max. 4, lambda minimum to infinity.
Fourth
Which
option.
option is correct?
Fourth.
Yeah. Ante maximum limit ledu. Maximum limit extends to infinity. Why? Because it is exponential curve. Can it is not starting from origin. That's why minimum limit is there. That is lambda. Okay. So here, this was the question given previously. Okay, no problem. You identified the answer. Fourth option is correct. Okay. Understood, Nana, this question?
Understood.
All of you?
Yes.
All right. Good. This was one question given. And keep in mind, these two wavelengths are not equal. Okay, 1 and 2. Originally, that formula is to be used to find out whom? Lambda
minimum wavelength.
Right. Minimum wavelength. Good. And you can understand one more point. In the curve, this part variation will be less. E part variation చాలా ఎక్కువ ఉంటుంది. ఇంకో పాయింట్ కూడా అబ్జర్వ్ చేశారు అది?
Yes, sir.
అందుకని approximately the lambda minimum and lambda of maximum intensity, we are writing the same equation here by doing some approximation. ఇప్పుడు క్లారిటీ వచ్చిందా?
Yes, sir.
అంటే సెకండ్ కర్వ్ తీసుకున్నా నీకు ఇలా వస్తుంది కదా నాన్న, ఇలా వస్తుంది కదా కర్వ్ నీకు.
అవును సార్.
ఇలా వెళ్ళిపోతుంది. అంటే ఇది మినిమం, దిస్ ఈస్ ద వేవ్ లెంగ్త్ ఆఫ్ లాంబ్డా మాక్సిమం. ఈ డిఫరెన్స్ తక్కువ, బట్ దిస్ డిఫరెన్స్ ఈస్ మోర్. అందుకు దే ఆర్ టేకింగ్ ఈవెన్ టు ఫైండ్ అవుట్ లాంబ్డా ఆఫ్ మాక్సిమం ఇంటెన్సిటీ ఇన్ ఎగ్జామ్, సేమ్ ఫార్ములా. Otherwise, those two are not equal.
In sir, they are taking approximately same.
Approximately same.
Okay.
Why?
Okay.
Because practically observed, this gap is very less.
Okay. Yes.
Otherwise, they won't ask in exam, no. Such type
Sir,
of
at all voltages approximation valid?
అంటే ఒక మరీ లో వోల్టేజ్, అందుకే వాడు 10,000 అక్కడ అడగడు, వాడు 15,000 20,000 దగ్గర అడుగుతాడు.
ఓకే సార్.
అంటే నీకు హై వోల్టేజెస్కి వెళ్ళే కొద్దీ ఈ గ్యాప్ తగ్గిపోతుంది.
అవును సార్.
దిస్ గ్యాప్. అందుకని అక్కడ అడుగుతాడు మాక్సిమం. వాట్ విల్ బి ద ఇంటెన్స్ వేవ్ లెంగ్త్ ఆఫ్ మాక్సిమం ఇంటెన్స్. ఓకే, దిస్ ఈజ్ ఇన్ ద ఆర్డర్ ఆఫ్ ఆల్. మీకు తెలిసిందే. V ఈజ్ యాక్సలరేటింగ్ వోల్టేజ్. V is greater than or equal to 10 kV, 10,000 volts. Discharge tube అప్పుడే చెప్పాను మీకు.
Yes, to break the breaking strength.
Discharge. Yeah. Good. Okay. This is one thing what they found, Nana. And here, when the accelerating voltage
Sir?
Is
Sir, then why will they use X-rays to scan the body, sir? Means to get that to know inside the body.
Okay, after yeah, I will tell now after completion of this part.
Okay, sir.
Accelerating voltage is less than 20 kV. Okay. The continuous X-ray spectrum will be means is observed. Okay. Suppose when the accelerating, when it is greater than 20 kilovolts, okay, like 25,000 kilovolts to 30,000 kilovolts, like if you apply, it is greater than 20 kilovolts, okay, along with continuous X-ray spectrum, it is obvious. Why? Because it has to hit the atom, lose some energy, and then penetrate into the atom. This is a common thing. So continuous is obvious. You surely get whatever the voltage is. Okay. So continuous X-ray spectrum along with this. One more spectrum is observed. This is important. It is called characteristic X-ray spectrum. Okay, here doubt will arise. Sir, why you are getting this characteristic another spectrum here, sir? Already we got one spectrum there. Okay, that we understood, sir. Okay, obviously the electron has to hit the atoms and lose the energy. That is a simple story, we understood. Okay, but here why you are getting another type of characteristic spectrum? That too, if you increase the applied voltage, sorry, accelerating voltage here, okay, beyond some particular value. For that, what they said, after penetrating the atom, it is entering into whom? The electron.
Another atom.
Okay, after entering into
nucleus,
the atom, it is trying to come close to the nucleus, na?
Yes, sir.
Okay, coming close to the nucleus means in the meanwhile, is that space empty, Nana? Here,
yes, sir.
this total space?
Yes, sir.
MTA, but someone is revolving. ఎవరో తిరుగుతున్నారు అక్కడ.
Electron.
The electrons are revolving. Na? First orbit electron, second orbit
Yes,
electron, third orbit electron, like many electrons are revolving. Na? So here there is a chance when this electron penetrates the atom, there is a chance while coming like this, suppose hits the electron revolving in the K shell, K orbit, first orbit. K orbit means first orbit. Then, after penetrating the atom, already lost some energy. Okay, it has, suppose the energy capable to capture this electron, means knocks out that electron from the orbit. Then what happens? Suppose this electron hits another orbiting electron and both suppose come out like this. Electron with one more electron, orbiting electron. Then what happens? That orbit is empty now or not?
Empty.
Yes, sir.
Okay. When an orbit is empty, that too lower orbit is empty, then what happens? From higher orbits, ఎవరైనా అదే చేస్తారు, tries to reduce their energy. So they try to come to the lower orbit. Am I right?
Yes, sir.
In nature, any substance, any matter tries to acquire the minimum potential energy. That is the concept what we learned from mechanics. While throwing a stone vertical upwards, why it came down, falls on the earth. There we understood. The stone has the minimum potential energy on the surface of earth. That's why it tries to come back to the surface of earth to attain the minimum potential energy. In the same way, electrons kudanu, when you come to the higher orbit, their potential energy is more, Nana. Already you know that concept from Bohr's orbit, Bohr's concept. So tries to acquire the minimum potential energy and they are very eager to come to the first orbit. So they try to jump from there to here. When an electron jumps from higher orbit to lower orbit, then what happens? Like Lyman
Energy
series,
is
Balmer
released.
series, energy will be released like that's what I'm saying. In hydrogen spectrum, they are called as Lyman series, Balmer series, Paschen series. Same type of series you can find here, depending upon the possibilities from where to where it is jumping. And that too, those energies of orbits are characteristic of an atom. Means you can find the line spectrum here, particular lines. Okay. So in that line spectrum, the wavelength is how much? This one studied by Moseley. ఇప్పటివరకు చెప్పిన స్టోరీ అర్థమైందా? Understood the concept? What I
Yes, sir.
Yeah. So that is possible only at lower accelerating voltages or higher accelerating voltages?
Higher.
Why? Because it has the strength to knock out an electron from the orbit, even though after losing some energy here while penetrating. Okay, na? Anduku they won't find this type of characteristic spectrum, X-ray spectrum at 10,000, 15,000, 20,000. Ikkada వాళ్ళు find out cheyali endukante akkada there the energy is less. That's why possibility is less. So is it clear, Nana?
Yes.
Clear, sir.
Yeah.
సరే ఇక్కడ
Practically they found at
సరే ఒకవేళ ఈ ఎలక్ట్రాన్ అంటే బయట నుంచి వచ్చే ఎలక్ట్రాన్ కి వెలాసిటీ తక్కువ ఉంటే లోపలికి ఆర్బిట్ లో యాడ్ అయిపోయి తిరిగే ఛాన్స్ ఉందా?
అక్కడ గ్యాప్ ఉంటే కదా నీకు తిరగడానికి.
ఒకవేళ హైడ్రోజన్ లాగా ఓన్లీ ఎస్ ఆర్బిటాల్ లో 1 ఉంటే ఇంకో దానికి స్పేస్ ఉంటుంది కాబట్టి అలా కలిసిపోవచ్చా?
స్పేస్ ఉంటుంది. ఆ ఎలక్ట్రాన్ ఈస్ క్యాప్చర్డ్ బై ద ఆటమ్ అనేది అది ఛాన్సెస్ ఉన్నాయా అంటే ఐ కెన్ సే దేర్ ఈస్ సమ్ ప్రాబబిలిటీ, కానీ ఛాన్సెస్ ఆర్ వెరీ లెస్ అంటాను. వై? బికాస్ అదొకటే కండిషన్ కాదు కదా. దేర్ ఎట్ దట్ టైమ్ ద వెలాసిటీ అంటే వైల్ కమింగ్ క్రాసింగ్ వన్ పర్టికులర్ ఆర్బిట్, ఎట్ దట్ ఇన్స్టెంట్ ద వెలాసిటీ which is creating the centripetal force should be balanced by the centrifugal force. Na?
Yes, sir.
A condition satisfy aitene it will try to revolve around the nucleus. Ante ikkada probability alochiste there is a probability to capture this electron by the nucleus kuda capture cheyochu depending upon the velocity. Okay, there is a probability to revolve around the nucleus. There is a probability to cross the atom. There is a probability after hitting the atom stop immediately. There is a probability to knock out an electron. Inni probabilities unnai ikkada manaki.
Avunu sir.
Now you understood my pain?
Understood, sir.
From that gain what we understood, suppose one probability if you take, what is that? Able to knock out one electron. What happens? We are going to discuss. Okay, no?
Okay, sir.
Practically they found this one first time at 30,000 volts, Nana. Ante 30 kV graph దగ్గర find out చేశారు దీన్ని. This characteristic X-ray spectrum. Okay, and they studied and they explained like this. So here, do you have any doubt in this explanation of forming the characteristic X-ray spectrum, Nana? Do you have any doubt?
No, sir.
No. Our class up to, Nana? 11:30 కదా?
Yes, sir.
11:35 అయిపోయిందా? Okay, then just I write one point and we will discuss about this characteristic X-ray spectrum tomorrow. Okay? So it is called characteristic X-ray spectrum, and here how you get this characteristic X-ray spectrum? When the striking electron knocks the orbiting electron, knocks out the orbiting electron. Okay, then the electrons from higher orbits Okay, jump to the lower orbit and emits the energy difference as line spectrum. It is the characteristic X-ray spectrum. Okay, that wavelength depends upon line spectrum wavelength depends on whom was studied by Moseley, what the result he gave, and what the revolution we found in modern physics. Tomorrow we will discuss now. Okay, no? Right, if you want the pages, you can take them. This is the first page.
Okay, sir.
This is the second page.
Okay, sir.
This is the third page.
Sir,
Okay, shall I stop it now? Yes.
సరే ఈ ఎక్స్రేకి ఇంకా ఇందాక ఆర్యన్ అడిగిన హ్యూమన్ ఎక్స్రే సంబంధం ఉందా లేదా సార్?
ఉంది
అంటే ఇదే
ఆ
కాన్సెప్ట్.
ఎక్స్రేస్ ఈ ఎక్స్రేస్
ఓకే,
వచ్చే ఎక్స్రేస్ లో ఏ ఎక్స్రేస్ ని మనము ఎక్స్రే స్కానింగ్ కోసం వాడతాం అనేది టుమారో డిస్కషన్ లో వస్తుంది.
ఓకే సార్.
ఏది వాడితే డేంజరు, ఏది వాడితే మనకి నో ప్రాబ్లం, నో సైడ్ ఎఫెక్ట్స్ ఉండవు. సైడ్ ఎఫెక్ట్స్ ఉండవు, దేర్ విల్ బి నో సైడ్ ఎఫెక్ట్స్. ఓకే,
ఓకే సార్.
అవి టుమారో విల్ డిస్కస్. ఓకే, బాయ్.